Recording has stopped. Started. Hello. How's everyone doing? Yeah. Pretty good. Pretty good. Should we start? Okay. So, Ekin, any announcements?
I guess just the homework. The last homework is due tonight, so don't forget.
Is it the last homework?
Yeah, it's the last one.
Is it?
Yeah, I
guess
think
it is.
so. I guess it is.
I guess it is. It's the last homework. It's exciting.
Yeah.
Anybody needs an extension? This is the last homework. We don't care. I think it's the most annoying thing that somebody gives you a deadline and then 5 minutes before the deadline, they tell you, oh, no, you got like 3 more days. Remember the talk, ISMRM talk? I said that, oh, it's like the deadline's today. Well, it wasn't. It's tomorrow. So they moved it. Frustrating. All right. Let's see. Who's missing here? Oh, Anita's here. That's okay. All right, we can start. Okay, so today what we're going to do is we're going to do the artifact show. Okay, so that's the plan. And the idea is to talk about artifacts, the sources of them, and hopefully be interactive and kind of see. And these things are very practical. They appear in in clinical practice, and it's well, we touched with the principles in class. It's sometimes it's hard to kind of put these things together. So hopefully this kind of will, what do you call this?
Dovetail.
The what?
Dovetail?
Dovetail? It's like when you put fingers together, it's like everything will come up together, All right, never mind.
Synthesize.
I guess there's not a word for it. All right, anyway, so that's kind of the idea. So yeah, it should be fun. This is actually some of these were given. So ISMRM, the Society of Magnetic Resonance in Medicine, has an annual meeting every year, and this was part of that. They have a lot of educational activities as part of that, not just research activities. So this is part of that. So a lot of the slides are credited for those folks, but I've kind of mixed and matched others as well. Okay, so let's.
Mickey, is that from the guest artifact session?
Yeah.
Yeah, cool.
Yeah, Who Wants to Be a Millionaire artifact session. The person that used to run this, his name was Wally Block. He's a great, funny guy. Also, same lab as that I came from Stanford, and but long time before me. Now he's faculty in Wisconsin, Madison, and he just has a very good sense of humor, and also he likes to prank people. So there's a story where you have to know this is part of the MR, I guess history. There's a story, Gary Gold, who now is the chair of radiology at Stanford, was also a master's student at electrical engineering back in the days when Wally was a grad student. And Wally was participating in this, I have to say that Gary was already an MD radiologist, right? So when he was doing that, Gary Gold. The story goes like this, that Wally was working on a project scanning elephant seals from close to Santa Cruz, they Año Nuevo Park, they bring the elephant seals. They want to scan them in the scanner. These are huge animals. I mean, like huge, right? So then he felt like pranking Gary a little bit. And then he comes to Gary and goes like, Gary, listen, I have this friend, she really doesn't take care of herself. And I mean, she has some problems. And we did an MR. Can you take a look? And then he started showing slices, but like axial slices from down and then going up. And then Gary looks at this, oh wow, she's really not taking care of herself, because the huge level, the amount of blubber, I guess, or the amount of fat is just insane on these animals, right? And he goes like, oh wow, she has huge and large spleen. And then the liver is a little bit very fatty liver, and it keeps on going. And it's just, and while he cannot even hold himself a little bit, but like he's trying to maintain posture. And he thought that when Gary will figure this out when it gets to the flippers, right? But when it gets to the flippers, then he goes like, oh wow, what pose she was like, was she going like this, or anyway. So that's the story. It's a good story. So Wally it used to run these shows, and obviously it was pretty fun. It was pretty funny. It's part of the MR culture. All right, let's start. Dun, 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 dun. All right. So I think the way we're going to do it is I'm going to show you an artifact, and how about somebody just raise their either digital hand or just like raise their physical hand if you have a camera. And thank you for those putting camera on, and thank you again for participating in the class, and thank you again for showing for class. It's nice teaching in front of people as opposed to a blank screen. Anyway, all right. So what is the artifact? This is an abdomen MRI.
It's aliasing.
Oh, so it's A. What just happened here? Yeah. It is aliasing. You're absolutely correct. Hey, where'd you go? You're on the left there. Why do you move down? He was here, and now he's there. I'm gonna move you back, okay? Because like it threw me away there. How do I move people? Okay, yeah, it is aliasing. Hold on now. But now, what causes the artifact? I'm asking you on the
Oh, B.
The field of view
Louis.
in the phasing code is too small. So which direction is the phasing code?
Left, right.
Left, right. And what do you see on the left, right?
That's where you see the aliasing from the edges.
So is that what you mean? Is
Yeah, right there.
that what you mean?
Mhm.
Okay. All right, right on. Okay, so third question, since you already
Wait,
are on. Yep.
I have a question. There's some other artifact here. Can you say it?
Where?
Here.
Well, I know I could probably see it, but
Yeah.
what is that?
I don't know. That's my question.
Yeah, that's probably a motion artifact.
Motion, but it's really localized.
Yeah, motion could be localized.
Okay.
I mean, it's a spread over there. It's probably like because of bowel. Actually, this is the, let's see, it's the liver and I think it's the stomach. So the stomach kind of, moves. I don't know. Sometimes you sit down, watch TV, and then suddenly go, yeah, right. So when it's kind of
What you
quiet,
had for dinner.
it's a little bit embarrassing. Yeah. Okay. So, okay, are you ready? So you know what, Fred, you're there. So how about you answer this one? How can the artifact be corrected?
Well, I'm not sure about A. If you swap the phase and frequency encoding, does this mean that you swap the FOV too?
If what?
The field of view?
No,
Did you
just,
change it? Or
no.
just the axis? So no. So I will go for B. Increase the phase encodes. No, I'm not sure what it really means. What does it mean to increase the phase encodes? I think that what needs to
Increase
be
the
done-
number of phasing codes, yeah.
Oh yeah, then. Well, I think that you need to increase the FOV.
Okay. So actually the answer is both A and B actually are both reasonable. B, you can increase the field of view, and that would resolve some of the aliasing, but it also would significantly increase the scan time, right? If you instead, can you hear me? Yeah.
Yes.
If you instead swap the phase and frequency, well, in that case, the image would be cut, right? At this point and here,
Yeah.
and so the aliasing will go away. And because this is the shortest dimension, you actually probably want the phasing code to be in that dimension. Now that said, there might be some issue with that because breathing goes up and down here, and breathing could be a problem in the phasing code dimension, because if you breathe, because the readout dimension, like if you basically will, it filters it out, but when you have motion with the during the phasing codes, then each phasing code is inconsistent with each other. And so you'll get kind of a spread across the phasing code dimension, and that basically will spread across the image. So it's a little bit, it's not completely clear what would be the best strategy. But the first thing I would do is flip the swap phasing of frequency. If the artifacts still show from motion, then I'll flip them and then increase the phasing codes. Does that make sense?
But if you flip them, you will both cut the image and get a lot of black area below and above the abdomen. No?
No, you can still do. No, it doesn't matter. The black area doesn't matter.
Okay.
All right. So yes, this is aliasing, and often aliasing is obvious, like you've seen before. And the solution is to increase the field of view in the phasing code direction, or really to swap the phase and frequency, like I said. So if this is the phasing code direction, you might see, stuff aliasing on top of each other, right? Now the thing is, sometimes it's not very obvious. Okay, sometimes it's not necessarily very obvious. And in this case, you definitely, you definitely identified the aliasing, right? Like you identified this and you identify that. And that pretty much aliasing of abdominal fat, that was obvious, right? But you actually didn't notice another aliasing that came. Can somebody identify it? It's very subtle. You actually need to know a little bit anatomy in order to do that, but there's something in the liver is not right. Okay, for those of you who are not familiar with where the liver is, that's the liver.
I can take a guess, but if somebody else wants to guess, then please go first.
Anyone else? Yes, Michelle?
Is it, wait, how do I draw? It's like in the lower left. It's like.
You
on
can
the
draw.
right.
I think you could go and like do how do you call this? Annotate.
Yeah, you click the view options that is in the menu above the screen, like on the top part of the screen. You click view options and then you click annotate.
Did that work?
It work?
I annotated it in blue, I think.
Nope.
Yeah, I can see it.
You can see it? Oh yeah, I
Yeah.
can see it too. Cool. Yeah. Can you erase it now?
Yep.
Thanks. Yeah, so what is that? Do you have an idea, Michelle?
Could it be the white thing on the right?
Well, okay, so pretty much this thing over here is the stuff that was supposed to be here, and it aliases to this point, right? So this kind of aliases here, right? So what about this? Where does this come from? Has an interesting shape.
Is a kidney.
Well, if if this alias is here, then you need something further away to alias it.
Is it the arm?
Yeah, that's right. But it's also far away from the coil, so its signal is lower. Right. Pretty cool, huh? So sometimes it's subtle. So this is the signal in the liver is due to the left arm, okay, of the subject. And because they put it, it's still away from the coil, but like it was still pick up the signal. And then because the field of view is not chosen, then it aliased in. Here's another example. This is I think I showed you this one. It's an IV tube that it's outside of the patient. Right. So this is the case where the IV tube is here. But then if you prescribe a smaller field of view, that IV tube will alias to this place. Okay. That's why IV tubes are always should be put very close to the body. Otherwise, they increase the field of view. Because they have, water in them. Okay. So this can be corrected either by increasing the field of view, phase field of view, but really you want to move the IV tube really close to the body. That's really the solution for that. Okay, so ready for the next one? Okay. What is the artifact that is common to both images? Yes, Tiffany?
It's B, chemical shift.
That's right. That's chemical shift. All right. And then what causes the artifact?
D, fat and
That's
water
right.
have different Larmor frequencies.
That's right. Because fat and water have different different Larmor frequencies, then they might be a shift in gradient in 2DFT or 3DFT or any Cartesian trajectory. The result will show as in the shift because frequency is often mapped to position due to gradients. But if you have a shift, then you would map the frequency to a different place because you think that it comes from the gradient rather than the chemical shift. Okay. All right, last one.
Question,
Oh, wait, question.
Yep.
what is the thing on the left?
Oh, this? It's probably you know, the quadricep or a cut through the leg.
Legs, okay.
Does that make sense? So that's the femur bone, probably in the middle. Lots of fat in the leg. Yeah, fatty legs. And so you've got fat over here, and then this is muscle, and then you got a shift. It could be an elephant seal. Okay, and then
Okay, I have a question too. So you said that this artifact is apparent in 2D and 3D Cartesian imaging, but what about non-Cartesian?
well, what about non-Cartesian?
Well, I would expect it to appear too,
But how? In the same way?
probably not. It will depend on the trajectory, right?
Yes, very much so. But usually if it's non-Cartesian, it would be some sort of a blurring.
Of a what? Sorry?
Blurring.
Blurring.
But it would not be just the chemical shift. Any then, basically whatever is not on resonance will be blurred. Okay.
Okay.
And
Thank
then let's see. Tiffany, right? You
Yep.
you all again. You moved. You know, stop joining or moving away.
Sorry,
Please. I mean,
it's because when I
it's not-
raise my hand.
No, it's not. It's not you. It's not. Oh, there you go. Keep the hand raised. Ah, can you unraise it? Oh, whoa. Oh, no, raise it. Oh my God, so much fun. All right, so the question is, how can the artifact be minimized or corrected?
I think maybe D, scan at a higher B0 field, because then the difference in Larmor frequency is smaller compared to the magnitude of frequencies.
All right, so here's a question. How is chemical shift measured? Is it absolute frequency?
No. So it scales with B0.
Right, it's ppm, right? So it's always a ratio, okay, depending on the field, right? So with increased field, actually, this gets worse.
I see.
Okay.
Well, my next guess is C.
Increased bandwidth or bandwidth per pixel. And that's absolutely correct. So if you increase the bandwidth per pixel, then each pixel would contain more bandwidth. Hence, any changes in frequency, let's say okay, so at 3T, the distance between fat and water is 460, something like that, 460 hertz. Yeah. And if the bandwidth per pixel was 500, the fat will shift, less than a pixel, right? But if the bandwidth is, 30 hertz, well, then it would shift 10 pixels, or actually more. It would shift, 40 hertz, it would shift 10 pixels. Okay. Does that make sense?
Yes.
So bandwidth per pixel will tell you a lot what's your sensitivity to chemical shift and distortions. So lower the readout bandwidth would actually do the worst thing, and increasing the resolution will actually not do much. Actually, it would make it also worse, because it would be bandwidth, like if you keep the bandwidth per pixel the same and you increase the resolution, then it would move more pixels. No, if you keep the bandwidth per pixel the same, then it's, forget what I just said. Okay.
I have a
if you,
question.
Yep.
Why does the shift only occur in one direction, like in the left-right direction?
That's a good question. Do you wanna? So which is the phasing code direction in this image, and which one is the phasing code?
I'm guessing that the left-right is the phase-in code because it's shorter, and because that's where the artifact happens, and things tend to happen in the phase-in code.
Okay, so anybody else? No? All right, so the chemical shift actually happens in the readout direction. And the reason is because the readout is not finite, right? Like the phase basically accrues along the readout. So if you think about it, when you read right to left in K-space, while you're collecting the data, the phase increments, and you got like frequency collected. So like this is not finite. Whereas if you do a phasing code, in the phasing code direction, the phase in this time and the phase in this time is the same, and the phase in this time and the phase in this time is the same, right? So the phase is consistent along along the phasing code direction, but it is increasing along the readout. Okay, because it's evolving. Does that make sense? Kind of. The head is moving too slow, and I don't think it's internet lag.
Kind of, that's correct.
So,
I
yeah. You want
I
to say
think
something?
as far as I remember, the chemical shift expresses itself as an exponential term, right? When we read K-space.
No,
it's not that
it's a
one.
complex
Yes.
exponential term.
Yep.
It's a complex
what I mean.
exponential term, which is phase pretty much, right? Complex
Yeah.
exponential, it's a phase component, and it increases along this direction, right? Because when you read basically fat, let's say water, right? Like the phase of water, as you move in K-space, doesn't change. The phase of fat increases linearly because it's a different frequency. And so linear phase is a shift. Linear phase in the frequency domain is a shift in the image domain, right? But in this direction, the interesting thing is, let me just maybe use a few colors: red, orange, yellow, green, blue, purple, right? Red, orange, yellow, green, blue, purple, right? That's how fat increments in terms of phase from left to right during the readout. During the second readout, you excite again, you go out in K-space, it actually is the same thing. It starts with a red, orange, yellow, green, blue, and then purple. So in this direction, when you compute a Fourier transform, then the phase is exactly the same across, of the fat image across the phasing codes. But it varies right to left, and that's why the shift is right to left. Does that make sense? Now, what if you have an EPI trajectory, an echoplanar? So echoplanar imaging, you do red very quickly, and then orange, yellow, green, blue, and then purple, right? As you move in K-space. Because you collect that, you collect things very fast. Right? So this is the short direction, and this can actually evolve over a long amount of time. So most of the shift in EPI would be in what we call, it's not really a phasing codirection because there's no phasing code because it's just EPI, it just goes back and forth, but in the slow direction. That's where the phase accumulates the most. And if we're talking about spirals would be red, orange, yellow, green, blue, purple, right? So it accumulates that way. And so the result is kind of a phase that varies radially. And that's why it causes a blur, because the inverse Fourier transform of a phase that's radial distributed, it's kind of like a spread, like it's spread function, it's very spread. Does that make sense? No? Any questions? That's the color of the rainbow.
Thanks, Mickey. It was really a very clear explanation. Also, I want to mention that I bought colorful pens for your course, and so far I managed to make my daughters not steal them, so I'm happy.
Oh, nice. Yeah, I have also colorful pens. It's white, and white is made of all the colors.
That's true.
All right. All right, next one. Ready? Anybody wants to volunteer first before I show you the artifact? Let's see who's risk averse and who's not, who isn't. Oh, you want to see the artifacts and then you're going to say, yeah? No, I want to volunteer. It's an easy one, I not promise. I promise, nah. You want to see it first? Fine. Oh, Rebecca. Okay, Rebecca. All right, fearless. What is this artifact? And let me just give you an idea what you're looking at. This is a cross section through a breast. In the top, you have an artifact. In the bottom, you don't have an artifact. And this thing over here, is a tumor.
My guess is bad fat suppression. No.
Yes,
Oh.
You're right. Isn't that what the sound, is about? Right? Oh, tin, tin, tin. Yeah, it is bad fat suppression. Absolutely. So there's a lot of fat in the breast. And you can kind of see that here it was suppressed, but here it wasn't. Okay. And so there was, and here the fat was suppressed nicely. You only see the water tissue, and then you can see the tumor much better because the fat was suppressed. All right, ready for the follow-up?
I have a question.
Yep.
Why is it not a flow artifact? Like the white area in the middle.
So this is not a flow because first of all, there's not much flow here. Flow artifacts actually appear very differently, but it's very obvious that, it could be that there are motion artifacts over here. So for example, but they appear in both images. So for example, this and this is a very blurred object. Anybody has an idea what that blurred object is?
It's the heart.
Yeah, that's right. And why is it blurred?
Because it's moving very fast.
Yeah, moving all the time. And so, yeah, so in that case, the heart would be What's the phasing codirection? Anybody has an idea? If you notice, this is the heart, but you see a lot of artifacts over here and over here. But you don't see artifact over here. So what's the phasing codirection? Cindy, you want to say something?
It's up down.
Yeah, it's up down. That's right. Because the inconsistency happens up down, and it's only limited to that area, and so it's going to flow. Whereas the readout is in this direction, so it is pretty. So the part of the breast is consistent over the readout. Okay, and then Rebecca, are you ready to the follow-up question?
Can I not volunteer for this one? I have something that I need to deal with right now. Sorry.
Okay. In the middle of class, that's great.
It's very
problem.
important.
Yeah.
Sorry.
Is it? Oh, very important. That's probably. What did we say is very important? What do you,
That was inhomogeneity. I think.
inhomogeneity. So she has an inhomogeneity problem. Okay, so anybody wants to volunteer? 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 Come on, we have only 40 minutes, so we're just spending time. Like if you make a mistake, it's okay. Thanks, Anita.
How about a poor shim?
There you go, poor shim. Absolutely, that's correct. So a poor shim, because if you want to suppress fat, often suppression of fat is frequency selective pulses. And if the shim is not uniform, or the magnetic field, and that's very important, it's not homogeneous, then different parts of the image will be suppressed differently. Okay, so that's great. Thank you. Do you want to do the next one?
Sure.
How would you fix the artifact?
You'd shim it. Use a higher order shim. Or you're thinking D, use all of them?
Well, I'm not thinking anything.
I would
Right
use
now.
a higher order shim first.
Okay, but let's say that doesn't work.
So then D, you could probably get the D.
Yeah. Right. So the option is, first of all, some systems don't have higher order shims. So for example, the system that we have doesn't have, like the G3T. So higher order shims means that you have other extra coils built in the system that allows you to have quadratic, third order, and so on functions of gradients that when you apply them, you would try to make the field more homogeneous. Targeted shim means that you are not trying to shim the entire volume, but you're going to tell the scanner to optimize the shim across the targeted volume only. And so maybe there you could do a big job because, it's hard maybe to shim everything, but really all you care about is the breast. Okay.
So I didn't
And
realize that we actually did shimming explicitly. I just thought the scanner kind of did it, was set up once, but do you actually have sequences that you can run to say shim it now?
Yeah, so a pre-scan would do shim, and sometimes you in the graphical interface you can actually mark an area where you're going to target the optimization to shim better.
Okay, I
So
thought
it's
the pre-scan was just sort of fixed.
Not necessarily. Definitely not on all systems. And then this answer is really true. Maybe you cannot. I mean, sometimes the field homogeneity is so bad that that's, there's just no way to do it. So it's all of the above. Okay.
Have you
So
ever
the
run into
explanation,
that?
oh yeah, all the time. Actually, Shreyas showed some of them in his talk, where you could see bad fat suppression in some areas. So here's the artifact explanation. I mean, you have the chemical shift between fat and water, that's constant. But let's say for different position, you might also have inhomogeneity of the field. And then if you now want to saturate, let's say fat, so you apply, let's say a frequency, like a saturation pulse that is, similar for all positions, but pick for a certain frequency. Okay. So the problem with that, yeah, it will suppress fat in this position, but actually it will suppress water in this position, and fat nor water will be suppressed in other places. Okay, so that's the issue. And when you do shimming, so shimming is kind of rotating the thing. I mean, it's like you can look at it like in different ways. It's either rotating the entire axis, that way, or rotating the shim that way, but that's effectively what it's doing. So if you shim very well, then you can actually select only fat if the field is homogeneous. Okay. Now the main issues with the breast is, this is the Z direction, right? This is Z usually. And so you have an object which is really, has a kind of abruption in the Z direction. And that causes a huge susceptibility artifacts, okay, because of air and tissue interface. And so that thing over here is really like that curve here, it's a killer. The shoulder, by the way, actually, I think that's what Shreyas in his talk, but the shoulder part is the same thing, air tissue interface in the Z direction. That's a big deal. Okay. All right, so bad shim introduces any off-resonance artifacts. So failure of fat suppression, so there are many methods. It could introduce distortion, and it could introduce blurring if you're using spiral or radial. Okay, so all of them. All right, anybody else now for the next artifact? You have to be really bold to pick that one. Rebecca, everything okay?
Yeah.
Any bold person? Like in terms of courage? Yeah, all right, ready? Job.
Yeah.
What is the artifact? Let me give you some background. This is a 3D RF spoiled gradient echo. So it's T1 weighted and it's very short TR. Okay. 6 millimeter thin MIP. MIP is a maximum intensity projection. So you take a few slices and then you look across the slices, and then you pick the brightest value. So that often shows blood, like if you have a blood vessel within a few slices, if you do a MIP, you would see the blood vessel across all slices because it will be the brightest part. And this is a contrast injection. So you inject contrast to the patient. You want to look here at an angiogram of the aorta, right? So this is the aorta. Okay, that's the aorta, and that's where it splits into the iliac arteries. So this is the aorta, comes out of the heart. And it's a 3D acquisition that is acquired with centrally ordered K-space. So if you think of 3D K-space, okay, the readout direction is in this direction. That's the readout. Okay. And so what you do is you start collecting phasing codes, slowly filling up the volume. So it's first you start in the center and then you grow out and then you go to the edge. Okay. But pretty much it's kind of like a sewing machine. You know, you go out in K-space, you go, you read a line in the center and then you read a line here and you read a line here, you read a line here, and so on and so forth. Okay. All right. So what this could be.
Can I ask a question first? What's wrong with this image?
Yeah, that's a good question. So if you actually look at the aorta is supposed to be a blood vessel, but I mean, it doesn't look like, I mean, there's like weird stuff around it, like the kind of like you see this wrapping around it?
Yeah.
Like it's supposed to look like just a nice solid vessel, but it has these kind of like edges on the side.
So could it, because of the motion, choose B?
That's an assumption. That's an assumption. Do you want to call a friend? Do you want to do 50-50?
Sure.
Okay, let's do 50-50.
I would choose C.
Which one?
C.
C, contrast timing error. Absolutely, this is correct. Yeah, so it's contrast timing error. Okay, let's actually, so okay, so this is the artifact. So what causes the artifact? Let me just give you an idea. I mean, this is acquisition over a few minutes. Okay, like 3-4 minutes. While the contrast, you inject contrast, contrast moves through the body and you collect data and you start from the center of K-space and then you go out. Do you want to call a friend?
I'll call Akin.
Well, try to call her. She's going to answer.
Hello, Akin. Can you help me out?
Hello. Bad.
Okay, it seems I have two friends in this class. Okay. All right, let me do some brainstorm
Oh,
here.
what happened to Ekin?
I have a feeling she was muted by someone.
Really?
Maybe someone who is hosting this meeting.
Okay.
That's interesting.
Anybody? Do you want to ask a friend?
Clara, do you have any guess?
I guess based on the hint about how we're starting at the center of K-space and then going out, I might guess A, that there's too little gadolinium in the central K lines.
I'll go with that. Yeah, makes sense.
Are you sure?
Can I choose A and C?
No.
No, okay, I cannot.
Are you sure? Dun, 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 dun.
Yeah, I'll just say, yeah.
All right. Ta-da! Very good job. Yeah, it's A. So too little gadolinium in the central K-space line. Okay. All right. How can the artifact be corrected?
I would choose B. So we started the acquisition from the center of the K-space, right? And
Yep.
from the last slide, we seem to start the acquisition too late. So we're only acquiring the gadolinium from on the peripheral. So we should start it sooner.
Yeah.
Yeah.
Ta-da! Good job. Yes, it's A. Start the acquisition sooner. Okay, let me explain. Let me explain the artifact.
Cool. Yeah.
Okay. So this is a ringing artifact. You see the ring here, and it's due to low gadolinium during the acquisition of the central K-space lines. It's another example over here. Okay. Now you inject contrast, and then you start collecting the central K-space line. The central K-space line contained most of the low resolution information, but then the aorta didn't actually get the gadolinium, and it only starts appearing at higher frequencies. Okay, so this is very similar to this Mona Lisa example, where if you acquire a full K-space, you get the Mona Lisa. If you acquire the lower part of K-space, you get a blurred image. But if you only get information from the outer K-space, then you get an edge map. Does that make sense? So what happens when you inject the gadolinium, it really doesn't, you don't capture, like, so basically you capture in the beginning an image which the aorta is not very bright. But then when you get to the higher K-space, it's brighter, and hence the edges are enhanced. And so that's why you get this ringing artifact. Okay. It's a pretty cool artifact, huh? All right, so here's the deal. You inject contrast here. There's a certain time that it goes till it gets into the arterial phase. Okay, and then after it goes into the arterial phase, it starts going into the vein, depending what part of the body, and eventually gets into the venous phase, and then basically, is cleared from the, eventually cleared. Okay, so first of all, there's arterial phase and then the venous phase after that. Okay, now when you start collecting the data too early, then you collect the central K-space line when there's really no contrast, and then you collect the peripheral K-space line where they actually the arterial phase. So that causes that effect. Now, if you move the acquisition such that the central K-space line are at the peak of the arterial phase, then you'll be able to actually capture the information appropriately. And then there's much less dynamic happening after that. I mean, there's a little bit dynamic, but it's much less. Does that make sense? Now, how would you know what the timing is? So what you do actually often is you take kind of 1 to 3 millimeter of gadolinium test bolus. Okay, so you inject a small amount of gadolinium, and then you acquire axial and sagittal multi-phase 2D gradient echo images. So not 3D, but 2D. For example, like this. So this is a sagittal 2D gradient echo, and you acquire them very fast. Now, every image would be like 1 or 2 seconds, as opposed to the 3 minutes that will take you a 3D exam. And then you would look at the aorta, and then you look at this pixel, and then you'd see at how long does it take to that pixel to actually enhance, and you'll be able to actually track how long for that particular subject, what is their hemodynamic response to the injection. And then what you do is you adjust the delay to where the peak is from the injection. Okay, this is how it's done in the clinic. Pretty cool, huh? So it's a tough spot to really kind of nail this timing. And so you have to, for kids, for example, it would be much faster.
What's the label on the x-axis there? Is that in seconds?
X-axis, yeah, it is seconds. Yeah, so it's about 18 seconds or so. Because it has to go from the arm, it goes into the right heart, then it goes to the lungs, then it goes to the left heart, and then goes to the body. Right, so that takes time. And that takes about 18 seconds. All right. X1. So this is a flow artifact. Who talked about flow last time? Who asked about flow? In the breast. Was it you up front? You want to do this one?
Sure.
So question, where do flow ghosts come from?
What do what?
So
Flow
these are
ghosts?
what,
Oh.
yeah, these are called flow ghosts because this is the liver and you're not supposed to see these bright kind of things and all that spread here in the liver.
So these are applications of the aorta.
That's right. So the aorta is pulsatile. You're collecting phasing codes of a slice. And as you collect those phasing codes, there is pulsatile flow. And so you get inconsistency of magnitude and phase across the phasing code direction, right? So that causes these ghosts in the phasing code direction. So these are view, it's called, so by the way, if somebody tells you a view of views, that's really phasing codes. So views are also considered phasing codes, just from the jargon that people use. So view to view amplitude variation or view to view phase variations, okay? And the idea is the following. You have an object, and let's say, let's say this is the object, and the object over time will be constant, except that the vessel might pulsatile, so it'll change amplitude over time, okay? The average of that is this. And so you can decompose this into the average and the time variation, okay? So the time variation would be really just the vessel itself, okay? All right, so now you collect phasing code one at a time, right? And the vessel modulates periodically, right? With a certain period. So if your image, if just the vessel changes periodically, and let's say it was a sine, exactly, a pure sine, well, the vessel will be multiplied by a cosine in the frequency domain. What does it multiplication in the frequency domain does?
Convolution in the image domain.
Right, it's a convolution. And convolution of what? What's the inverse Fourier transform of a cosine?
2 deltas.
2 deltas, right? So it is a delta and a delta that is convolved with whatever the vessel is, right? So it would result in replication. And hence you got yourself these ghosts. And you can actually tell, if you know exactly the timing of how many phasing codes and you see where the ghosts are, you can actually tell the heart rate of that. Because if the heart rate was fast, then the cosine would be faster and the ghost will be further apart. If the cosine was slow, then the ghost would be closer. Right?
I have a
So
question.
if the variation was, something like that, then the ghost would be actually here. Yeah.
Do we have a specific lingo when we say the word ghost, or is it a general artifact word, or does it mean a flow artifact?
A ghost is whenever you see something more than once, the same object more than once in an image. That's usually the terminology. And that can occur because of flow. It could occur because of aliasing. It could occur because of motion. It could occur because of phase errors.
So for instance,
many-
our very first image that had aliasing.
Yeah, that's aliasing because it wasn't a replication of some object, right? Like it was something outside that came in, right? So that's different than a ghost. That pretty much it's a replication of the image within it. That's often, but sometimes people will say, "Oh, this is an aliasing ghost." I don't know.
I have a question as well.
Yep.
We were mentioning that the vessel itself in the previous slide gets like darker and brighter. Does that
Yeah.
happen because the spins are physically moving like along the blood vessel?
All right, so yeah, that's right. So what happens is that like the slice itself is being knocked all the time, right? So it reaches a certain steady state, which is the magnetization. It's much lower than M0, right? Because it depends on T1, right? So when new spins come into the slice because of the flow, they have not seen the RI, they have not been saturated. It's just full magnetization. And now they've been knocked down, right? So that is then they'll become brighter. Now it's a pulsatile flow. So now the blood kind of halts and it's being knocked down. And then again, new spins come in, it becomes brighter. Does that make sense?
Yeah, thank you.
Now, if you have a modulation, yeah.
Sorry, I have a question too.
Yeah.
So I have a gut feeling that this ghosting is because we're not sampling in the right frequency in relation to the frequency of the pulsatile object. No, is it not like a violation of the Nyquist criterion?
Well, you can think of it in many different ways. If you would, yes and no. It's a little more complicated because you really, sometimes you don't want to resolve the image. Like if you did spatial temp, you could try to gate. How do you deal with this? You could potentially gate the acquisition to the heart rate. So effectively, you would acquire every phasing code at the same phase of the heart rate, and then basically the blood will have exactly the same value, right? Because you either capture it when the blood is in, or where you basically that's what would happen. Like you will get some new blood comes in, and so on and so forth, right? But then you can't really do that well with T1 weighting, because with T1 weighting you have to keep on going, right? So so you'll have to. I guess you could do it. You throw the data, and then you just you keep the data. Like you just do the same RF. And then only collect really data at certain time points in the cardiac cycle, and then RF, collect again data. But that would lengthen the acquisition significantly. We're talking about 256 lines. It's about a second every heartbeat. That's 256 seconds compared to, let's say, 5 millisecond TR. That is a long time.
So what you're saying here is that we can't avoid this artifact.
No, I didn't say that, but I'll show you examples how to mitigate with it. We didn't get there.
Okay. Sorry. Thank you for the explanation.
Yeah. Thanks for the question. Now, if the modulation is not periodic, then the Fourier transform of this function is kind of spread, right? Like it's high bandwidth, so it's spread. And so you'll get kind of like a streak because it's a convolution with something that's very spread. So you don't necessarily get something very coherent. So if you have a blood vessel, like that is really coherently pumping, then you'd be able to see, that. But if not, then you'll see a streak. And in fact, if you would change actually the ordering, I mean, even in this case, if you just change the order randomly of K-space lines, then it's kind of like randomly shuffling the sinusoid and you'll get the same effect, right? It will be also spread out. So the fact that you're getting a very coherent ghost is because you're collecting lines sequentially. But if you would kind of jump randomly between them, you would kind of shuffle this randomly, and that would result in something that looks like this, and then the artifact would look like that. Okay. So here's so what can you do to deal with this? So first of all, gradient produce velocity dependent phase shifts. So the fact that you actually have the gradient on, and you have some flow, then the spins will see kind of an increasing field as they move, and so that will cause a phase shift. And what can you do is you can kind of try to minimize those effects with the more complex waveforms that try to avoid that. The other ways to deal with this is what's called spatial saturation. So if you know that the blood is coming from above, what you could do is, if the blood is coming from either below or above, what you could do is you can saturate the slice before it. So the reason that I got this pulsatile flow is because nothing is touched below. And so new blood comes in and it's pulsatile. But if you actually you do saturation of the blood below, then blood that comes in will be already saturated and will not produce a signal when it enters a slice. And it's called also black blood imaging, because the blood would not have a signal because you've saturated it. And you could either do it on both sides or just one side, depending on the type of flow. So that would minimize this significantly. Like, see here, there's really no flow effects. Okay, but the aorta is dark. Does that make sense? And so you'll have to apply kind of like a 90 crusher to saturate the two slices, and then you do a excitation and imaging. And then crusher, excitation, imaging, crusher, excitation, imaging. So it costs you some time. And of course, RF. Does that make sense? Now, another way of doing this is doing averaging. So averaging, this is 1 average, this is 2 averages, this is 4 averages, and this is 8 averages. So averaging helps. It reduces this artifact because whatever doesn't move increases with intensity, wherever any incoherent artifact kind of behaves like noise, and it doesn't grow as fast because it doesn't add coherently to each other. Like noise increases with square roots, right? And signal increases linearly with averaging. So as you average more, then you reduce the effect of blur of the ghosting, but it doesn't really completely eliminate it. Okay, so often people will do averaging just to avoid this type of an artifact or to reduce it at least. The last thing, and that's kind of what you said before, Efrat, is gating. Gating is synchronizing the acquisition to the motion, for example. So this is an acquisition where now there's motion, not flow, but you gate, you don't gate, you just collect, and you see all this blurring and the ghosting that comes from the chest. You see the chest is very bright, and you see kind of like a replica of the chest, kind of like going into the body. But if you only collect data at certain points of the respiratory cycle, well, then you avoid that, because that is consistent. The image is consistent. The chest is going to be exactly the same spot. The last thing that you do is you try to match the phase encoding order with the respiratory phase. So this is interesting. So let me try to draw it to you. It's called ROPE, or respiratory order phase encode. Let's say this is respiratory. Okay. And let's do again red, orange, yellow, green, blue, purple, right? So you pick this part of the respiratory to be red. you pick this part of the respiratory to be orange. You pick this part of the respiratory to be green. And you pick this one to be, I'm not going to draw blue, so I'm going to do purple because blue is not going to work here. Okay, and this is purple. Okay, so you divide the parts of the respiratory cycle into bins. And now let's find a place that we can draw a K-space. So we'll draw a K-space here. And let's say now, whenever we're in a red region, sorry, let's say whenever we're in a blue region, a purple region, we're going to collect lines in the center of K-space. Okay, so now we start breathing more and we reach this respiratory. So now we're going to collect, this part of the respiratory. And then when we reach, let's say the orange, now we reach the orange over here. So we're going to collect kind of data up here in K-space. And now we get into red, and red is going to be like, further away. So now we're down to orange again. And so when we reach orange again, we require, these lines. And then when we're down to green now, we're going to collect, the green lines. And when we're down to the blue, we're going to not the blue, the purple, we're going to collect, this. So you kind of see the area place in K-space is kind of correspond also to the respiratory phase. And that causes, that reduces the ghosting artifact. It still has blurring, but it's just more smooth, because the inconsistency is not very sharp. So it's kind of like a kind of some weighting in K-space. So it causes blurring, but not necessarily ghosting. Does that make sense? And this is called rope. So the order that you do things in K-space makes a big difference on the artifact. All right, so we're almost done. This is slides from that, but I have a few more. So this is from second midterm in 2011. Did we get that question already? No, okay, cool. So these are two images acquired. One is acquired with an 8-channel head coil. The other one is acquired with a body coil. And the echo time is 1.1 millisecond. TR is 8 seconds. And then the flip angle is 90. And the question is, what is the dominant source of contrast in this image, in the body coil image? So you have to look at these parameters. Let's start with the TR. Is TR short or long? Long TR, right? Okay, so do you have full recovery after 8 seconds? Unless you're carbon 13, natural abundance, you're pretty much good. Water is like maximum 2 seconds, so 3 times that's 6 seconds, that's plenty. Okay. What about the echo time, long or short?
Short.
Short. So a lot of T2 star or T2?
Little TT star.
Very little. So what is the major source of contrast here then? If it's not T1 and it's not T2.
Proton density.
That's right. Beautiful. Proton density. Now the question is, what is the difference between the two images and what are the source of the difference? It's the same parameter exactly, but they look different.
SNR?
SNR is one. Definitely the SNR is different. There's other things though I see here, right?
Is it that 1 in 4 in the head channel coil or much closer to the array?
Yeah, that's right. So it's B1 receive in homogeneity, right? The receive coils, you know, this element is really close to this part of the object, and hence it's gonna has a much higher SNR, much higher signal, and that's why you have variation. Okay, and this is just due to the coil's sensitivity. So the coil sensitivity is not uniform. You know, whatever is closer will have a higher signal. Okay, but overall the SNR is much higher. All right. Let's see. All right, this is the last one, I think. Yep. So this is a saturation recovery sequence where the echo time increases and the repetition time is, you know, 1.5 seconds. So pretty long repetition time. So this would be mostly T2 weighted. And you see the bottles here. And the question is kind of what are the right T2s for each bottle? And I gave you some hints. Where's the bottle? Yeah. So this one has a T2 of 250. It's pretty bright. See, stays bright. What's the one that is the shortest?
Bottle 3.
Yeah, bottle 3, right? Like it's already dark here after 6 milliseconds, and then it's just pretty much gone, right? So bottle 3 is about 6 milliseconds. The next one after that,
The second one.
bottle 2, that's right. Bottle 2 kind of disappears also. The next one.
Four.
Yeah, that's right. 4, right? It's this is bright, but then it becomes darker, and then here it disappears, right? And then you can see it's like 60. So, you know, yeah, so it's pretty close to it. And then the next one after that, anyway, you get the gist pretty much. Pretty cool, right? Okay, the last one. What is this sequence for these exact same bottles? Actually, what's the artifact? Do you see the artifact? What's the artifact? What's the artifact?
There's blurring.
Folks, I gotta go. Blurring, that's right. In which
Especially for
direction?
fast T2 in the up-down direction.
That's right. Fast T2 in the up-down direction. And for the short T2, right? For the short T2, you got more blurring. That's right. Any idea? So let me just give you a solution opposed to a hint. Actually, no. In order to get blurring in one direction only based on T2, that means that there needs to be variation of intensity while you collect K-space, right? Because if you have, let's say, some intensity variation in this direction, right, in one direction, but not the other. The other is constant, right? So that intensity variation could be more significant with, with different T2s, or, with longer T2s is actually going to be constant. Okay, so different bottles will experience pretty much different blurring based on their decay. Okay, so if you have some sequence that is centrally ordered, that you collect first this line red, and then orange, and then yellow, green, blue, purple, right? While the sequence is being, while magnetization is being decaying, then you'll get this type of weighting. So this case is a fast spin echo. It's a multi-spin echo acquisition, right? Because in order to be sensitive to T2 and not T2 star, right? There's no shift. By the way, there's no shift here. If it was an EPI, echo planar, you would also see some shift or some, it's T2 star effect, but this is T2. So it's a multi-spin echo acquisition where in the first spin echo, you acquire the central lines, and then you acquire the outer lines and keep on going and acquire many spin echoes. It's called fast spin echo. And so because you acquire a fast spin echo, then the signal over time kind of drops for the short T2. But if you do it centrally ordered, then you would get blurring. Does that make sense? But the blurring is only in one dimension. You see, actually, it's really sharp in the other direction, which is kind of interesting because there's very little decay during the readout. The decay is, in the phasing code direction. Does that make sense? Thank you, folks. We're done. Next week, it's our last week, so work on your projects, and we'll also sign up for project presentations. Okay, thank you. Bye.
Thanks, Mickey, for a great lecture. It was really cool.